So anyway, Dr. Soltani, thank you for joining us. I met you at a conference in Orlando, and that's how I came to know about your work. And since then, that was last year, and since then we have been in communication, doing some work in digital pathology. So thank you for accepting to give a presentation and share your work in this space. We're all excited to hear the talk, and please go ahead. Yeah.
Oh, thank you so much for a great introduction. I also I'm very happy that I was invited and talk about my latest research and the group and the ModeLab latest research. The topic that I have selected for today's talk is, as we talked about digital pathology, but I work on different application domains as well. As the name suggests, we are going to talk about AI-based machine learning in digital pathology. And just to give you an overview of what we do in the lab, I want to give you just quick introduction of ModeLab, Machine Learning Optimization and Data Lab at Marquette University, which I'm the director. So we work on different application domains. I have been working on digital pathology in the past 7 years, and that was most specific. Like I have done other medical imaging as well, but mainly digital pathology. But I also work on a smart power grid, and I do a lot of network science and complex systems as well. And in terms of the theme of the research, we do graph AI, a lot of graph-based. Everything we had done so far is so much graph-based. And then robust defined learning, uncertainty-aware learning, generative AI and diffusion models in a smart grid and also digital pathology, distributed machine learning, and also optimization theory. And also
do this.
So I was on the third slide, actually.
Okay, third slide. Okay, let me go to the third one.
Thank you.
This one? Yeah.
Yes, thank you. No, the third one. I think one more. We went to when we start from the tissue samples from like a biopsy or a surgery, then the sample is collected, but then we need to preserve the sample, and they preserve it and make sure that it's not it's going to be in formalin, and make sure that it's not damaged or anything or degraded. And then they create the slides through the machine, and those slides, once they are generated, is not clear, like the color, it doesn't have anything, so it's not clear to pathologists. They cannot really do any diagnosis. It needs to do through some staining called H&E staining, where the samples are going to be stained. I cannot show you with my pointer, but actually when you see there is a color in there, so this is where H&E is generated. And then after that, those H&E slides are actually what the regular pathologists look at it over the microscope, through the microscope, and try to do the diagnosis. But when it becomes the digital pathology, it goes through the scanner, and then they actually scan those whole slide images, those slides, and then they get the whole slide images that can be used for basically AI-based machine learning on digital pathology. So this is not like all the hospitals do it that way, but this is like most of the hospitals are trying to get to that point to make everything digitized. And then now the focus of this talk is like AI-based, basically digital pathology, where how we can do computational pathology using these whole slide images. So can you go to the next slide, please?
Yeah. Okay. This one.
So I want to just mention some of the computational pathology challenges that I'm going to address in this talk. So one of the key issues with these whole slide images is that they are really large. They are gigapixel resolution slides, and they need basically a very, very specific method to be able to process them. So also, it's important for the pathologist, like it's not necessarily like radiology or other medical images. There is a spatial context in that needs to be considered. And also another issue that we have is H&E staining varies across different labs and hospitals. So if I want to basically summarize some of the main challenges in computational pathology, one of the things is there are always image artifacts. So there will be like tissue folds, there may be blur, there may be staining irregularities, and those issues happens during the scanning. Also, there may be a stain variability because even in the same hospital, they may have different scanners, or even with the same scanner, they may get different whole slide images with slightly different colors and everything. And also different hospitals and everything. And then there is this domain shift or out of distribution, meaning that if, for example, you get the data set and you train your model using the data set in your hospital, and then you want to basically use your model in another hospital, or let's say using another whole slide images from another scanner, it doesn't necessarily do well because these are considered as out of distribution data. So this is another issue we have often in pathology. And then there is no uncertainty quantification for these models that they talk about. So basically, there are a lot of deterministic models which give you confident but wrong predictions. So you really want to be certain about or know how much is the uncertainty. And then obviously there is limited annotations. And one of the things that I have put on the top is adversarial vulnerability. And we are going to talk about it. All these I'm going to address in this talk. So basically, adversary could be like someone intentionally tries to manipulate the data set that you had on cloud, the whole slide images, or this could be not necessarily basically intentional. This could be like someone actually like due to a scanner artifacts or something, there are some noises on your data. But typically, I mean, I really think that both of the cases can be captured by adversarial vulnerability and robustness. And then how the traditional deep learning models work, actually most of them fail. If you want to think about, this is an image, we use convolutional neural network like a CNN. This is not gonna fit well for whole slide images. This is because they divide them into patches. First of all, the performance is not good for like such a large images. Usually they use ensemble methods if you want to think about the convolutional neural network. On the other hand, convolutional neural networks divide the whole slide image into patches, and these patches do not consider any spatial relationship between tissue regions, which is critical for understanding disease progression architecture. So these were the motivation of the work that we looked at, and actually I'm going to talk about. So can you go to the next slide? Tell me if I'm too fast. I'm just trying to give the background.
Yeah.
I think I'm going to.
Oh, so shall I just display everything? I know it will be difficult to do by line.
So the thing is, I'm just trying to compare quickly because I know most of you probably are familiar with convolutional neural network. They're widely used for image classification. And what they do, if you want to do it for all slide images, they do smaller patches and they try to process this whole slide image as patches.
Oh, sorry. What happened here? Stop sharing. I'm going to share again. 1 second.
That's exactly what happened to.
Yeah, I think so. Something is not right today. Yeah, that's okay. I will. I think we have a very patient audience. Let's see. Oh, it is actually in this. Oh, this is where the problem was, I think. Okay. I don't know how it just jumped.
Okay.
Can you see it now? Yeah.
Sure. So I'm going a little bit fast if there is somewhere that you
want. Please do. Yeah.
So I just want to compare convolutional neural network had these issues, but graph neural network captures the local and global contextual information. Actually, we proposed this in ICAS 2023. We considered like whole slide image as a graph and proposed this, and then we published a journal version later. So it captures a spatial and a structural relationship between the patches, which is important for the diagnosis. So it's really more powerful, and also it's easier to process the large data set. So can you go to the next slide, please?
Okay, there you
And
go.
then if I want to just quickly give you an introduction what graph is, as you're familiar with graph, like V represents the set of nodes, E represents the set of edges, and X is the node features. And there are a lot of node real-world graph examples. If you think about the LinkedIn, like let's say, or so any social network like Facebook, there are nodes that are people, edges are relationship, molecular graph could be atoms, edges are chemical bonds, and then recommendation system. We have road network. I have used it a lot in a smart power grid. And then we have like set of nodes, and we have edges, and then the features of that. So can you go to the next slide? And I want to show you how we can construct the graph from whole slide images. So what we need to understand is when you have whole slide image scan, this is the first image on the left is what you will see. So this is not really ready to go. You need to do segmentation first to remove that white area around it. And if you remove that white area, you see that green area. So that's like what you really need. This is your whole, I mean, the tissue sample that you're looking at. So then you want to basically make it into a small patches, for example, 256 by 256. And then what we do, we create those patches and then use k-nearest neighbor to create edges among these. So nodes are patches. And then we use k-nearest neighbor, for example, 4 nearest neighbor, 5 nearest neighbor, those that are basically in terms of like you can consider like closer to that as the nearest neighbor, and then you assume there are edges among them. So that will generate a graph like this. And I have the next slide, which is even more clear. And you start with like the whole slide image. You see, I am putting the patches with like position information. So you do not just throw them. It has to also incorporate the position information. Then you pass it through the encoder like a ResNet or anything to get the features out of these basically patches. And once you have the feature set, you basically do the k-nearest neighbor and get the graph constructed. Can you run the, yeah, thank you, yeah, all of them. So basically, each patch is treated as a node, and edges are created based on a spatial proximity, and then node features are extracted with a deep learning backbone, like you could use ResNet or anything else. It doesn't have to be like. So then you create that graph. Now you have a graph with nodes and edges. And then if you ask me what common...
Yeah, I'm sorry. This is very critical, actually, to know how you're translating the image into a graph network, right?
Yes.
So nodes and edges, I'm familiar with that. Are the edges being constructed using k-nearest neighbor?
Yes.
Yes.
I see. So once you create those feature set, then basically you find the spatial proximity among those nodes. And then you say, for example, 4 nearest neighbor, 5 nearest neighbor. We did like 4, 5, 8, up to 8. And we saw that 4 was the best for this case. But another problem, we did 8. So you do 4 nearest neighbor. And then among those 4 nearest neighbor, you create an edge with like weight 1. Let's say.
And do you have directionality in this, or you're throwing away the directionality?
No, it's just undirected.
Undirected. Okay. All right. Okay. Let's keep going.
Sure.
Yeah. Oh.
Oh, that's yeah.
Let's see. Okay.
And if I want to just I want to just quickly tell you like what is GNN versus CNN. You know that there is this weight update in CNN, but the only difference, I just want to mention what is the difference of CNN and GNN. There is this graph adjacency matrix that is incorporated here. So you see A. So A is incorporating the structure of the graph now. So basically all the relationship information is incorporated. So it's not like all the nodes are responsible. Basically any neighboring node and those structure that you have in the graph, those are really impacting your learning and updates of the weights. So if you can go to the, next figure. Yes. So I have a very quick example for you. For example, look at node 3. If there is update for node 3 for the weights and things, so only nodes 1, node 2, node 5, and node 8, which are neighbors, are responsible for the updates of that specific node. So that is really efficient if you think about it, and also you are considering neighborhood information and spatial information.
Mm-hmm. Are there algorithms that directly do these things, or do you have to go through every patch and then figure out?
No, there are algorithms. There are like some algorithms that there are a number of like now GitHub things that you can just use. Yeah.
Oh, okay.
But initially, when we were doing it, we did everything from scratch. But now
that is amazing. That's a lot of work for the whole
image. 5 years ago when we were doing it, it was like.
Oh, I see.
So.
And maybe you're going to say this later. Did you find a great advantage with the graph neural networks as opposed to the normal CNN?
Yes, absolutely. We have another work that I haven't presented here. That was the initial work that the reference was initially there. So we showed that about 10% or 8% increase. But now we are not talking about CNN. We are talking about transformers. Now we are in transformer era. CNN is like probably that old thing. We absolutely had a better performance, and we did everything graph-based after that. So.
Okay, good.
So I just want to mention some of the artifacts that are commonly seen in whole slide images due to scanning, storage, digitization. Some of the common corruptions are you can think of like brightness, saturation, hue shifts, or pixelation, blurring, bubbles, or even there are markers on the slides if you have seen. So there are so many issues like that. Those artifacts are very common, and I want to consider them. So we are like IEEE, like this is IEEE, so we consider everything as noise. So I call it noise. So this is one of the noises that I want to handle, let's say. And then if you go to the next slide, and let me know if I'm too fast. I'm just trying.
No, keep going. Yeah, I will interrupt you if I don't follow up. The other people can also ask questions in the chat. Yeah.
And then if you, so the thing is, there is also, if you can go one more, there are so many. Yes. So there can be also adversarial attacks. So I want to explain adversarial attack to you. If you think about like autonomous systems, if there is a stop sign and there is like a snow, or like it's or if there is like fog, so it may see that differently. So the autonomous system cannot identify. So the adversary is not necessarily, if you want to think about adversary as someone who intentionally does something, it can be unintentional. And then you can think about someone that really intentionally wants to attack your data. So it's very common in medical images that you think about attackers that they want to attack like data in the cloud or like in other places. So it's very, very timely to think about it as well. So there may be attacks on the data, and I'm going to talk about the attacks to the images, whole slide images, as well as attacks to the model. So these two could be different. And in any case, you come up with incorrect diagnosis, and also additional scanning may be needed, incorrect treatment, and also insurance claims. These are the things that might happen if you have like adversarial attack. And one thing you should remember is that deep learning models are very fragile and vulnerable to attacks.
Mm-hmm. So I want to ask you one question here. The attacks, can you expect attacks like somebody inserting a tumor in an image, and then that could really lead to a wrong diagnosis?
Tumor, like
in an image, yes.
So typically the attacks are considered as something that you cannot easily see by your eye, but that is very visible, so you can easily identify that, right?
Oh, okay. Yeah. Well, some mitotic figures somebody can insert.
That's an attack. That's an attack. But then I'm saying that even in the worst case, if you go to the next slide, and you bring all of them. So this is this is a panda if you do not have an adversarial attack. But if you do have adversarial attack, if you can go one more. So if you have adversarial attack, this is actually classified as gibbon. And this is one of the well-known papers. This is the FGSM adversarial attack, which is adding a small noise to the data, which is not even visible to the human eye. So like if you give the whole slide image with a little bit of attack to the pathologist, they cannot identify it. I mean, that the beauty of the attack is this, that you cannot know, but then this is identified when you use AI. So AI will give you the wrong diagnosis, but the pathologist won't. But that thing that you mentioned is like probably visible with the human eye, and the pathologist can easily say that.
Okay, got it.
So, and then adversarial attacks can be on the graphs as well, like some edges may be removed or added, or like the node features may be manipulated. So these could be any, and there are a lot of work and in literature that show how we can attack the graphs. And I also have some publications on that. So like we can also like focus on how to attack graphs or like the model. Can you go one more, please? And then this is showing that, for example, you have the whole slide image, it is clean, but then after the patch encoder, if the constructed graph is manipulated, then obviously the decision is going to be, the diagnosis is going to be changed.
Okay.
So I just want to give you a brief summary of adversarial attacks. So one thing about adversarial attack is you need to remember what is the attacker access, what is the attacker goal, and what is the attacker knowledge. So attacker access is like, is it going to be manipulating at the test time only to evade the detection and alter the predictions, or is the attacker also corrupting the training data at the learning time as well? So that's the question that you need to, when you have a problem statement and modeling, you need to clarify which one of these options you're working on. Also about attacker goal. Okay, does it want to force the model to make a specific node like, or a specific incorrect prediction? So for example, this type of cancer to be always predicted incorrectly, or this type of thing. So like, is it a specified, or like any wrong prediction would be make him happy, you know? And then another thing is attacker knowledge. Does attacker has knowledge of the model or data or training process? What is the knowledge that has, or attacker has just limited knowledge or no knowledge of the model? Because this really changes the game. So in this work, if you go one more, please. So we are working on it. Oh, sorry, if you go back.
Oh, back? Okay.
Yeah. We are doing evasion attack, meaning we are just considering the prediction attack at a prediction time, test time, and also it's non-targeted, so any incorrect prediction would count. And then it's a black box, meaning that the attacker has limited or no knowledge of the model. So that's how the problem statement is.
Okay, next.
And yes, so if I want to talk about adversarial attack in digital pathology, based on the model that I suggested, it can be image level attacks, which involve adding a small perturbations directly to whole slide images. As I showed you, there are different methods, and this perturbation can cause the network to misclassify tissue patches, or it can be at the modeling level. Like when you generate the graph at that graph level, so there will be like attacks on the graph level, so that will be manipulated, and that's not something that you can even see and notice. So we are going to actually model both of them and see how that impact. And then the goal is not, I mean, the contribution is not like how these attacks, there are known attacks that are used for images, known attacks for like graphs, but the contribution is how to robustify the AI model to basically take care of these attacks.
Okay.
So the two common attacks that we considered and are very popular, one is FGSM, one is PGD. I don't want to spend too much time on that, but the FGSM is a fast gradient sign method, which is like adding like a small noise to the data once, is not like based on the gradient. It takes the gradient and then add a small noise to the data based on the gradient value. And there is another method which is stronger than FGSM in terms of attack, but it needs multiple steps and adds noise in multiple steps in capital T iterations. And these are like known methods and is not the contribution. It's just that we are using those to attack the data.
Okay.
So the contribution of the work is algorithm robustness. So basically, sorry for the noise, it's just, there is a denoiser and there is a transformer and classifier that we have. So the denoiser, we start with the convolutional neural network. Then we have the denoiser, which is we have design, and we have pooling layer, and then we make everything ready to go to transformer for final classification. So I'm going to talk about each of them in detail. So the denoiser block is actually very important to remove the noisy part, or let's say any adversary added part or artifact. Anything that has been added and is unwanted as noise is removed by this basically the denoiser block. And this is part of the basically entire block. So I'm going to talk about how this denoiser really works. This is based on a work based on the untrained neural network FIRE framework from 2022. So we got some of the ideas from that. And if you go to the next slide, I'll show you the details. So what it does, this denoiser, is recovers the clean graph signal from noisy observations. So XT is the clean data, and N is noise, and X is the total noisy, or let's say adversary attacked, or like you can think of artifact. So it can be that. And then you have the noisy graph signal. And what we can do is we do random initialization. The random initialization would be with a zero mean and unique variance, meaning Gaussian noise. And then you have a model exactly using that graph structure that you have, but with the initialization of that random initialization of the noise, like the white noise. And interestingly, the reconstructed signal would be very close to the actual signal rather than the noisy one. And it's really hard to believe because it's starting from random noise, but think about it. There is a loss function here that is norm 2 squared, and x minus x hat, that loss function is always tracked. But there is a key here that you need to do early stopping. If you do late, like you're going to catch up the noise. But in early stopping is important because generally GNN or GCN learns low frequency components better. Like when X is basically when the actual data is very smooth compared to noise, which has a lot of fluctuations and is high variance. So you need to do early stopping to be able to get the actual data. So the stopping really matters in this algorithm. And then the data set that we used the prostate cancer data set, 10,000 whole slide images, 5 Gleason grades, Kegel challenge it was. And you know that the biopsy samples were graded by Gleason scoring. And lung cancer subtyping is another data set that we used, 1,345 whole slide images, and they were TCGA data set. Again, I don't know if you're familiar, it's a very well-known cancer genome atlas.
Yeah, I am very familiar with that. Yeah. So there's huge amount of data there, cancer data. Yeah.
We use it for a lot of work that we do, and we often use those different types of data they have. So for the image level adversarial attack, we did use 10% attack with FGSM, 25%. By 10% or 25%, I mean how many portion of the entire whole slide image we have attacked. 10% of that, 25% of the image, or 50%. So 50% is really large, right? So, and then similarly with PGD, we try to attack and see, and then 10% and 50%. And we compared with graph neural network, we use with graph attention network, with vision transformers, and we already see that this is working much better than any of the state-of-the-art methods, because it has a denoiser block, which is a signal processing based method. And if you go to, this is for the prostate, and for lung cancer, similar thing holds with no attack. The first one is showing no attack, then we have 10%, FGSM, then we have 25%, then we have 50%, and you see that still it is outperforming by at least 2% than any of the top methods. So we were expecting that vision transformers work really good, and still we're happy that we see that the proposed method is outperforming that.
So the vision transformers, you don't use the graph-based vision transformer, or is this a vanilla?
No. We use the graph for the initially. Everything is based on the graph.
Yeah.
Nothing we're doing with, but if you go back to that previous slide, you see that we had the convolutional neural network, we had the denoiser, then we had the features, and then we created the tokens, and the class tokens sent to the transformer. So if you don't have the denoiser, you send the features from the GCN to the transformer.
Okay. So basically, introducing the denoiser has given you this additional improvement. So that means it removed the noise, right? Denoiser is basically taking out the noise of the input image, right? Yeah. Okay.
Exactly. And we can also perturb the number of edges and the overall graph, and then as a graph level attack, and it's 10%, 25%, 50% of the edges versus no perturbation. And we still see that for both Panda and long data set. This is working much better than we didn't try it with vision with transformer, but we just did it with two of the other methods. So, and also we did for the artifacts that I mentioned to you. So things like blurriness, brightness, brightness, hue, motion, saturation, pixelation, and defocus. So we have checked it with denoiser and without denoiser. So without denoiser, you can see the performance is not as good. So about 2-3% difference. And then you put the proposed denoiser, you see the performance absolutely improved. And I'm comparing with all the state of the art and anything that it could be relevant. There is no work that has done this thing, or either adversary or artifact in digital pathology, but we try to use the best models that are there to compare how this can be handled. And also for long data set, again, 10% noise, 50% noise is very similar. Again, it shows that significantly improved. And then you see the brightness. Some of them, there is more impact for, let's say, brightness, let's say for, let's say hue, or it is different. So you can see how much the denoiser is in helping. And
sorry. I think I may have moved too fast. Okay, here it is.
No, go ahead. No, go ahead. And also, this is Kappa score and other for the prostate, and comparison with the lung cancer as well for the artifact paper. So again, we have also looked at the Kappa score. So for out of distribution, robustness, one thing you should remember is out of distribution matters as well. I mentioned to you that you may have different scanners, you may have different hospitals. So you want to have a lot of papers that you see, they come up with 90% accuracy or something, and they're happy about it. But when you try the model on your data, you see it's not as good. So the reason is the data set that you have is out of distribution compared to the data that they have trained their model. So this auto distribution shift is very important in digital pathology. There are different scanners, there are different hospitals data. So this needs to be actually addressed very well. So what we have done is we have actually identified out of distribution whole slide images, as well as also robustify the model for out of distribution data as well. So there is a model that I am proposing here. And of course, we have other papers and models. I'm just showing you one of them. So if you go to the next slide, I'm just skipping more details. So explainability for graph neural network is, and also for any deep learning, is something that everyone is talking about. They want to have, when you have a diagnosis, when you have a prediction, you want to see which regions are responsible for this prediction. So for example, I have a work that it shows exactly to the pathologist, let's say, because of this region, this is grade, let's say 3. Or grade 1 of the cancer type this. So this explainability is something everyone is working on. There are tools out there for convolutional neural network, for graph neural networks. So you can go and check, and then, I mean, we can use them to show which regions are responsible for the diagnosis or the prediction. Two of the tools that are there is our GNN explainer and GraphLine, which are specific to graph neural network. GNN explainer shows which part of the graph are most responsible for a graph neural network prediction, because we have a graph. So you want to know which subgraph, or what is the smallest graph structure, or what are the smallest graph structures that are actually, if you keep them, you get the same prediction. So that's like really important concept that I really love this paper when I saw it. And then there is GraphLine, which is local explainability, which identifies the most important node features responsible for a prediction. So, and that focuses more on interpreting the tissue or graph characteristics that drive the model decision. But what I am going to use these two is not like showing you the regions or anything, but I want to basically use these tools to robustify my model. I'm not going to use it in a way that you're familiar with. Can you go to the next slide?
Okay. Oh, sorry.
I think
I made it. Oh,
yeah.
Okay, there you go.
So I want to use the explanation and go to the robustness. So I want to isolate decision relevant subgraphs or subgraph, and use the GNN explainer to uncover the smallest subgraph or subgraphs that are strongly support the model prediction. So find those subgraphs, then find the most important keynotes and say, like, these keynotes, these nodes are the most important. How do we find the most important nodes? I use network science ideas and use the degree centrality, between centrality, and those type of centralities. And I show that node centrality is the most useful for sorting those nodes in the network. And then the next thing is I use GraphLine. After I sort those, I use GraphLine to find the top features that contribute most to the prediction. And after that, you're able to basically get the final features. We use the local smoothing, or we can use global context injection. So what is local smoothing? Instead of the node features that you got, you can replace them with the average of their neighbors. So you look at the neighbors so that it adds to the smoothing rather than just whatever you have got. And then in terms of global context injection, you can just blend the node features with the overall graph mean embedding. So basically, you can look at the average of the graph and then basically a little bit change yours with the average. So it's kind of like making it more relative. And then the gradient, there is a gradient type of perturbation, like more of a adversary and robustness thing. So if you go to the next, the first, if you click, the first one is the graph in.
Oh, this is going to know everything.
A lot of, so I'm just showing the steps here. So the first area I can show.
Yeah, let's do this very quickly. Yeah.
The first part is graph construction. Whatever I showed you initially, we are constructing our graph. The graph is constructed. Now I give it to GNN explainer. If you click one more, the GNN explainer is now taking care of choosing the most important subgraphs for us. And then if you click one more, I do node degree centrality to sort the most important nodes. And then after that, we do graph line to identify the most important features of the node. And then we can use that augmentation, like use the one hop method or average mean or like any of those methods that I mentioned to get the final features, node features.
Okay,
so
great.
This is the augmented graph that we can basically use. And if you use that, it shows that the performance significantly improves if you go to the next slide. But before I go to the solution, in terms of ranking nodes, there is this node degree between a centrality and closeness centrality. Node degree is basically shows how connected, basically more connected to tissue neighborhood, gives you higher spatial influence. So that's really what it means. So the number of neighbors and everything. And then between the centrality identifies basically bottleneck nodes in the graph. So it's really important, but we showed that. And also we have closeness centrality, which measures overall reachability, some of the nodes that are central to the basically graph. But we tried everything and we saw that node centrality is the most important.
Okay.
So the data set we have used is Brox, and for in distribution and for out of distribution, we use different data sets. We use SLN, BREST, and Chameleon 16. Again, those are public data sets. And for implementation, we use PyTorch and those. And then we have checked uncertainty and also out of distribution performance. If you go to the next. The first thing is we want to see what is the train and test accuracy if you use any of these augmentation methods like adaptive mean, one hop, and as you can see, adaptive mean is giving us the best, a one hop neighbor actually, a one hop neighbor gives us the best test accuracy. So that's what we stick to. So we first tried it and see which one is better. And then eventually, now you want to see how it works with out of distribution. It means that your trained data set is different from test data set, as you can see. So you see some of them are Brox data, and then some of them are not. So if it is the same data, it means it is in distribution. If it is different, it means it is out of distribution. And then I'm using different methods. And as you can see, by far, like this method, like 84% compared to 50-60% is far better for out of distribution data than other methods that are out there. I mean, the numbers are still low. It's not 90, but we are not expecting 90 in this.
Yeah, this is good. Yeah.
Yeah.
But having introduced those node centrality, closeness, and yeah, all of that is helping. Yeah.
Yeah. So, and then
basically with that approach, you're really filtering some of the unwanted data, I think, right? That's how you have improved the performance. Yeah.
Yes, that's exactly what we try. And then by augmentation, we are just trying to make the model be more robust with more unseen data, like with more changes at training.
So, Doctor, how many more slides you have? Just
I have a few more. I mean, I can go fast and just show you the results for this. You have 4 minutes.
4 minutes, yes. I wanted to open up for questions because some people may have good questions. So let me see where.
So this is about, if you can go, this is about uncertainty estimation. And because there are different scanners, how do we basically model and learn uncertainty? If you go quick, I'll show you some results. Maybe go next, please. Go next. So if you can go next, I'm trying to avoid like If you go, yes, so this is yes, if you can go again, so I show you the architecture. So what, oh, sorry.
Oh, sorry.
So the thing is, we are trying to, there are a lot of methods that we can actually use to identify uncertainty, which like Monte Carlo dropout is one of them, which is actually, you do the dropout in the training, but if you do it in testing, it's like you are actually playing with your brain a little bit and see if I give you different questions each time, are you consistently giving me the same answer? So the Monte Carlo dropout is a very, very famous one to do uncertainty quantification and confidence. But what we used was multi-head prediction. So basically we consider different heads and basically multi-layer perceptrons, and we run this through all these and then get the average prediction. And also for each of them, when you get the prediction, there is also a variance which shows that how much you're deviating from that. And then based on that, we try to identify the uncertainty. But it wasn't just the graph neural network. We use graph attention network, which is actually putting attention on different areas or regions of the graph, as well as GraphSAGE, which is also doing sampling among the neighboring nodes, which are also very important for like something large like whole slide images. Sampling is very important. So we use that multi-head GraphSAGE and GAT to do this. And if you go to the next slide, I do quick. Can you go next? So these are the results, and you can see that our algorithm, a multi-head GraphSAGE, we did multi-head graph attention. We did different heads. We did 3, 5, 4, but 3 worked the best. So with different number of heads, you have to try it. And if you go next, please, I go just one slide I show, and then I'm done. I think that maybe we should go for questions because there are like maybe 5, 6 more slides.
Yeah, let's do this then. So if people want to stay for another 5 minutes at least, I can stay on another 10 minutes actually. I do have quite a lot of questions. Let me open it up to the audience. You can, if you have access to the chat, I think you do have access to the chat. You can come online and ask questions. So yeah, see, we don't have too many people. So.
Let me see. There is a question, or
yeah. Let me ask you a question if you don't mind.
Sure.
All right. Thanks for a great lecture, Professor. And my area of working and experience in power systems, so smart grid, you have some research going on smart grid. So I have a few questions related to that. So you see opportunity to transfer this methodology, graph-based learning, to smart grid applications, given your background in network science and power systems?
Yes, so actually we have actually 4 recent papers on that in a smart grid, and one was we used for fault detection. So it's in IEEE transaction in power systems, which was recently published. We also did motif detection. There are 3 more that is under review. So there are a lot of opportunities that you can consider, because by nature, a smart grid is a graph. And then think about all those currents and voltages, and also you can also identify the structure itself. So there are so many problems that you can think of in a smart grid. But I suggest you look at my recent paper. I mean, it's not recent, it's just from last year, I guess, which IEEE transaction power system. We did multitask learning using graph neural network for fault detection and localization in a smart grid. But there were a lot of other things and papers that we have done in a smart grid using graphs.
Okay, great. So that's my next question. Since both pathology and power grid can be represented as a graph,
yes.
What lessons from graph learning in digital pathology might be transferred to power system monitoring and anomaly detection?
So your question is transferring?
Yeah, transferring methodology.
What sort of ideas here or approaches can be transferred to power systems? I think that's what the question is.
I think a lot of these things that we do in in pathology, the adversary attack is one of the important things that, we definitely want to, that's one of the things we work and we have a recent work on that. So you want to basically robustify power system. You want to, why a smart grid? We still have cyber physical issue and like because of the cyber physical system security, right? And the security of a smart grid is the most important. Adversarial attacks and those graph things are really important.
Okay, so I believe you're modeling both physical power system and cyber aspect as well.
Yes, that's like I started with like more physical, and now we're more doing cyber.
Yeah, I would like to invite you for talking on power grid application, whatever your research work in my PES and IES society.
Yeah, definitely. I would be happy to. I would love to. So just you have my contact info, and please, yeah, I would love.
By the way, yeah, Alkesh is he's the section head, so he oversees all of the IEEE operations for our section. All the chapters within this. Right. So that's really good. If you can present.
Yeah, that's great. Yeah, thank you.
If you can invite her, physically, that is even better.
Absolutely. Are you distinguished lecturer, professor?
Pardon?
Are you part of IEEE DL program? Distinguished?
Yes.
Okay, yes. I'll look into that and I'll connect with you and I'll invite you here. Possibly, physical. We are planning for mini symposium in October, around end of October.
Which location are you?
Sorry?
Which location are you?
We are based off upstate New York, Schenectady.
Oh, okay. Great.
Yeah. So I'll check your availability if the time align. Probably will virtual or in person. I'm inviting other speaker as well. Sure. So we will arrange that. But thank you for your time. And this is emerging area at
CIS.
Thank you so
much.
And we develop use some machine learning concept and the prediction, right? Pattern recognitions and prediction of the next state of the system. We already have that, but this is great to learn on other aspect as well. Thank you.
Thank you so much. Thank you.
So, other question, Professor Chang, do you have any questions? Yeah. I see you online. And you've been doing quite a lot of work in this space.
Yeah,
so,
the other drone came out. Yeah. So thanks a lot. Yeah, I'm Ming-Ting Chan from UAlbany Computer Science. Yeah, I another work I'm doing has overlap. It's just not pathology, but on medical imaging and industrial inspection as well. So this adversarial attack and defect detection. And the OE detection, I also have work on that. Yeah, very good talk. Thank you. So my question is, do you see any say foundation model applied to digital pathology? By foundation model, I mean say for the meta segment anything 3 model, right? So by training a large set of data, then you can apply to this specific task. I mean, the people are doing this foundation model for industry as well.
Yes.
So, yes. Yeah.
So we are doing foundation models right now. Yeah.
Okay. Yeah.
We are working on. And also one other thing that our paper has been submitted that is under review. We got the minor revisions. Is we are doing untrained neural network, which just for finding out of distribution.
Okay. I see. I see. Yeah. I see.
Yeah. This will be very useful. Yeah, this will be very useful because I'm trying to set up collaboration with Dr. Chang, and he will be exposed to pathology very soon. So
that would be great. Yeah, I think also this foundation model. I mean, the other idea is to apply this vision language models so that you can produce this natural language description of the whatever model you are predicting, right? So uncertainty, trustworthy, all of this, you can convert it into natural language, right? So for the human expert to better contribute knowledge, to provide feedback or,
Right.
explainability. I think that would be also
so there is a paper that is actually, to our knowledge, the first paper that had been actually going over like vision language models for digital pathology, and I can share. It's actually going to be published soon. So let me see if I can share it here, the link. And it's very comprehensive, like everything my student went through. How can I share something here?
Google start properly, you can.
Yeah, that has been a problem, right? I have to stop sharing, actually. Maybe then you can.
No, if you just put it in the chat.
Chat, there is a chat or something.
If it's a link, you can just place that in the chat.
Yeah, so I'm trying to find the chat.
Chat is on the right side, bottom right. Chat with everyone. You see that?
I can email it to.
Yeah, you can email it to me.
I put in my email in the chat. So thank you. Yeah, if you can, share, that would be great.
Send it to you and then you share it. I think I have the. But this paper is going through on foundation and vision language models in pathology. Is, as I told you, it has taken 1.5 years for review, but it's getting published. So, but it is in archive. So I just shared it with you. Hopefully.
Great. Yes.
Can you share it? If you received it, Dr. Chang, can you share it with me as well?
Oh yeah, sure.
No,
yeah.
I didn't share. I shared it with you, Lalit.
With me? Oh, okay. I will forward it to Dr. Chang. Yeah. No problem.
Wonderful.
If anyone else was interested, it is in my Google Scholar. So it's called A New Era in Computational Pathology, a survey of foundation and vision language models. So it's a very long.
Yeah.
Okay.
I think this under this umbrella of this trustworthy AI, the privacy, security, fairness, all this is very relevant to this pathology. I mean, so you mentioned this adversarial attack. That's the security part, right? So the adversarial attack and defense, right? And then do you protect the data or do you protect the model, right? So the fairness, right? So I think the distribution of data, right? So I think across the gender, countries and cultures, ages, that's important. And I think the robustness you mentioned is already detection, right? So I think all of this is under this big umbrella that I think it's pretty trendy topics.
This is because there are so many models coming out, but the issue is now how we can make sure that they are robust, we can trust them, they're trustable. Like those answers are still.
It's also like learning from noisy labels, less labels, right? So this is like transfer learning or some domain interpretation. This concept drift. I think all of this thing is pretty relevant as well. That when you consider like degraded data or noisy data, incomplete data.
Yes.
Okay, great.
Thank you so much for that. Yeah.
Thank you. Yeah. Any other questions people have? See.
And thanks, audience, for patience with those.
Yes. We had a lot of issues, right? So in the presentation, back and forth, not sharing. So that's okay. That this happens, and remote presentations are always risky. But I think I have a lot of questions. I'll catch up with you afterwards because I don't want to have other people stay online. So, but definitely this was a very good presentation. I can see the value this creates because images, you don't have to have a perfect size. It can be any piece of image, irregular shape even. So so that's the one we can use as inputs. So whereas in the normal CNN world, you cannot do that. I am very delighted that you could come and remotely and spare your time. Thank
you so much. Thanks for inviting me.
Thank you.
Thank you.
Take care, everyone. Bye.
Thanks very much.
Bye. Thank you.
Bye.